Good evening, everyone. Today we are going to see about the calculation of liquid nitrogen consumption in a manufacturing process. Usually, you'll be having the regular utilities like RT water, chilled water, and chill brine, and the operating temperatures are going to be dependent on, like the utility temperatures are going to be dependent on the operating temperatures. Like the chilled water is applicable only in the range of 10 to 30 degrees, and above 30 degrees we'll be using RT water. And if the process temperature is if the process requirement is up to -10 or so, we'll be using the chill brine. And beyond, if we want to cool the reaction mass further, or if we want to perform any operation beyond -20 degrees of temperature range, we'll be going with liquid nitrogen. And we are going to have an internal coil inside the reactor to use the liquid nitrogen facility to reduce the losses towards the environment. And today we are going to see a specific case of reaction and the liquid nitrogen consumption for the specific case. I'll start with the heat of reaction. So let's say the heat of reaction the heat of reaction is almost, let's say, 3000 kilojoule per kg of KSM, and let's say this was taken from the RC1 report. The plant batch size is 500 kgs. So here the total heat liberation is going to be a product of heat of reaction versus and the batch size. This is in kilojoules, and for convenience purpose I'll be converting these kilojoules into kilocalories. And now first of all we need to understand the cooling capacity requirement. The cooling capacity requirement in terms of TR. So to get this we need to divide the total heat liberation with 3024. So it's almost 119 TR. And this total heat liberation which is available in kilocalorie shall be called as demand, like the process demand we can say. And we are going to solve this problem using the energy balance. And before estimating the consumption of liquid nitrogen, let's take few properties of liquid nitrogen. Usually liquid nitrogen will be available in the range of -196 to -210 degrees centigrade. So let's say this is a temperature scale. So here it is approx -210 degrees centigrade, and this is -196 degrees centigrade, and the phase is liquid here. And from here, if any further thermal energy is being transferred from this liquid nitrogen, it will turn into a gas. It is nothing but a boiling point. The vertical arrow indicates a phase change, that is from liquid to gas, and the energy which is being liberated during the phase change is nothing but the latent heat, and this latent heat is approx 200 kilojoule per kg. And the specific heat, that is the temperature required for a change of 1 degree centigrade, is nothing but the specific heat, and the specific heat of liquid nitrogen is around 2 kilojoule per kg degree centigrade, the CP value. So as mentioned, the specific heat of liquid N2 is going to be 2 kilojoule per kg degree centigrade, and I'll try to convert this into kilocalories by dividing with 4.184, and this is going to be kilocalorie per kg degree centigrade. And the latent heat is almost 200 kilojoule per kg, and I'll be converting this into kilocalories by dividing with 4.184. That means during a phase change, liquid nitrogen can release almost 47.8 kilocalories of energy. And now we know the demand, so here we need to estimate the supply now. So energy balance is nothing but equating demand and supply. So the equation for supply in this case is going to be mCp delta T plus m lambda, and I'll try to take the m as common. Cp dt plus lambda. So here the value of m we need to determine. M is nothing but the liquid nitrogen mass, and as part of energy balance I'll try to equate this thing. So just before that, let's try to include all the values here. M multiplied by Cp is 0.48 and the delta T is, the maximum delta T for liquid nitrogen is going to be almost 14 degrees, that is 210 minus 196, it's almost 14 degrees, and as a worst case I'll be taking the liquid nitrogen is available at 200 degrees, so I'll be taking a delta T of only 4 degrees. Plus here the lambda is 47.8, and this is the equation we got. And as part of energy balance, let's equate demand and supply. So here the demand is almost 3,58,509 kilocalorie, and the supply is this. So M equals to 3,58,509 divided by Cp into 4 plus 47.8, and this is going to be almost 7,212 kgs of liquid nitrogen. So this is the theoretical thing, and here as a worst case scenario I have taken only, like the liquid nitrogen I have taken only at minus 200 degrees. So usually it is going to be at minus 210 degrees, and considering the losses I have taken it minus 200. So as the delta T is going to be almost 4 degrees, so we got around 7,212 kgs. So this is how we need to calculate the theoretical requirement of liquid nitrogen. And apart from that, considering the other losses like the pre-cooling of a internal coil which is available inside the reactor and all, so let's again take almost 5% of the total value. So this is including losses. So losses is nothing but the consumption of liquid nitrogen which is for a non-value added purpose. So I'll be multiplying this with 1.05. So approx 7,500 kgs of liquid nitrogen is required to perform the reaction and to compensate the energy liberation of almost 3000 kilojoules per kg of KSM. So this is how we need to estimate the liquid nitrogen consumption. Hope you like the video. So if any queries, you can write a mail to me at pharmacalci823@gmail.com. So if you like our video, please subscribe to our channel and share with your dear ones. Thanks for watching.